This is skill practice 24 with Lewis dot structures. And Trog, I hate him. He's a little Indian. Yeah, you know how to finish that. But all right. First question. We're going to draw the resonance of CO3 minus 2. The first thing we need to do is figure out how many valence electrons each element has. So we're going to multiply by their subscript and the column in which they're in. So for carbon, what we're going to do is it's in the fourth column, and because it doesn't have a subscript next to its name, that means we're going to multiply by 1 because there's only one of them. So we multiply by 1 and 4, and we're left with 4 valence electrons for carbon. Now we're going to do this for oxygen. And oxygen is in the sixth column, so we're going to take 6 and multiply that by the subscript next to oxygen, which is 3. So when we multiply by 6 and 3, we get 18. That means we are left with 22, because when you add 18 and 4, we're left with 22. But because it says CO3 is a charge of -2, we have to add 2 more electrons because it's a negative charge. So that means we get 24. So because we add 22 and 2 up, and you get 24. Alright, so question 1 continued. Alright, we're going to draw the resonance of it. So we're going to draw first we're going to draw the first molecule with just single bonds, and we find out that doesn't work because we get 26 molecules instead of 24. So when we use a double bond, actually for one of the oxygen molecules, it works. We get 24, which is the right amount. But now we have to draw the resonance. So when we do this, so let's say we drew the double bond on the right oxygen. So then when we draw resonance, we're going to have to draw the double bond on the bottom oxygen and the left oxygen, because the bond is actually shared by all 3 technically in a realistic standpoint, but we can't do that really drawing, so that's how it actually works. Alright, for question 2, I kind of answered it in question 1, but in order to figure out the bond order, all you need to do is count the number of bonds, and the double bond counts as 2, so that's 2 plus another single bond plus another single bond, that's 4. And then you're going to divide by the areas that they can be bonded to, and there's 3. When there was 3 oxygens, the carbon could be bonded to. So 4 divided by 3 is 4/3, or 1 1/3. Alright, now we're going to have to draw the structure for carbon dioxide, or CO2. And when we do that, we're going to do the same thing we did for the CO3 minus 2. We're going to count, which column each molecule is in, and then the subscript next to their letter. So carbon is in the fourth column, and it doesn't have a subscript next to its name. We're going to take 4 multiplied by 1, and gives us 4. And we're going to do this again for oxygen. So it's in the sixth column, and there's 2 for the subscript. So we're going to take 6 multiplied by 2, and we get 12. 12 plus 4 is 16 valence electrons. And when we try and draw CO2, we're going to use all single bonds first. But when we do that, we get 20, which is too many. So now we're going to try and use a double bond on one of the oxygens, and when we do that, we still have too many. We get 18. So we try and put another double bond on the other oxygen, and that gives us 16, which is the right amount. Alright, question 4. I'm going to comparing the structures for CO3 minus 2, or CO2, which is the strongest and which is the longest. Well, single bonds are the longest because the attractive forces between them are the weakest, so it doesn't have to be held together very closely. So the CO3 minus 2 actually has the longest bonds, because this is the only molecule that has single bonds. And CO's 2 bonds are hardest to break because the bond is second order, because there was 4 bonds, there was 2 double bonds, so 2 plus 2, that's 4 bonds. And then there's 2 areas to bond, so 4 divided by 2 is 2, and that's bigger than 4/3. So that is why CO2 has the hardest bonds to break. And fill in the blanks. Let's see. In general, the stronger bonds are shorter than weaker bonds, or the shortest of the bonds, because the attractive forces holding those bonds together are a lot stronger. That's why, because the electrons are so close and they're being exchanged between the molecules rapidly. And in general, double bonds are longer than triple bonds, because, as stated above, the attractive forces between the two are weaker, so it doesn't have to be held together as tightly. And bonds with lower energy, or bonds with a low energy, are weaker than bonds with high energy, because, as I said, the attractive forces are weaker, so it's easier to break them. And that would be skill practice 24.